This is the first of two videos I'm presenting on simple harmonics dynamics. Here we show a simple harmonic motion diagram. The top set of dots is a motion diagram for a simple harmonic motion going to the right. The bottom set of dots is a motion diagram for a simple harmonic motion going to the left. At x equals 0, the object's speed is as large as possible, but it is not changing. Hence, the acceleration is 0 at x equals 0. So let's define acceleration in simple harmonic motion. Well, as before, acceleration is the time derivative of the velocity. So that's d dt of the velocity, which is d dt of minus omega a times the sine omega t, which is equal to minus omega squared a cosine omega t. So a sub x is equal to minus omega squared x, because we know that x is equal to a cosine omega t. In simple harmonic motion, the acceleration is proportional to the negative of the displacement. So now we begin our discussion of the dynamics of the simple harmonic motion of a mass on a spring with no friction. We know from Hooke's law that the force exerted on the spring by the spring is equal to minus k, the spring constant, times the displacement delta x. Since the spring force is the net force, Newton's second law says that this net force is equal to minus kx, where x is the change in the position, and that's equal to m times the acceleration in the x direction. From this we see that the acceleration is equal to minus the ratio of the spring constants to the mass times the displacement. And since a sub x is equal to minus omega squared x, the angular frequency must be omega equal to the square root of k over m. In Quick Check 15.9, a mass oscillates on a horizontal spring. Its velocity is v sub x, and the spring exerts force S of x. At the time indicated by the arrow, which of the following 5 choices is true? The correct choice is answer D. The velocity is 0 because the slope of the position curve at the point in question is horizontal, or 0. So the velocity is 0. And f sub x must be negative because the position, must be positive, because the position is negative, and therefore the acceleration must be positive, and f sub x is equal to m times a sub x. So that's why it is positive. Now we consider the same question, but at a different time, as indicated by the arrow. In this case, the slope is negative at the time in question, and so the velocity is negative. And since the position is equal to 0, we know that the acceleration must be equal to 0, and so the force must be equal to 0 as well. Now we'd like to consider vertical oscillations. We start with an unstretched spring, and then we attach a mass to it and allow it to hang a vertical displacement below the original position, delta L. Here the motion for a mass hanging from a spring is the same as for a horizontal simple harmonic motion, but the equilibrium position is affected by delta L equal to mg over k. We know this is true because when we do a free body diagram of the mass, we have, shown on the far right, the force of the spring acting upward, balanced by the force of gravity acting downward. So kx, or k delta L, must be equal to mg. And then solving for delta L, we get mg over k. As an example of vertical oscillation, in 15.6, we do this problem involving bungee oscillations. An 83-kilogram student hangs from a bungee cord with a spring constant 270 newtons per meter. The student is pulled down to a point where the cord is 5 meters longer than its unstretched position, and then released. Where is the student, and what is his velocity 2.0 seconds later? In this example, we model a bungee cord as a spring, and we consider vertical oscillations that are simple harmonic motion, where the oscillation are shown in the figure are between plus A and minus A from equilibrium. When we solve the problem, we note that although the cord is stretched by 5.0 meters when the student is released, this is not the amplitude of the oscillation. The oscillations will occur around the equilibrium position, so now we have to begin by finding the equilibrium point where the student hangs motionless. The cord stretch at equilibrium is given by equation 15.40, delta L equal to mg over k, which we calculate to be 3.0 meters. Stretching the cord 5.0 meters pulls the student 2.0 meters below the equilibrium point, so the amplitude is equal to 2.0 meters. That is, the student oscillates with amplitude 2.0 meters about a point 3.0 meters beneath the bungee cord's original endpoint. The student's position as a function of time measured from the equilibrium point is given by the equation. The vertical position is equal to 2.0 meters times the cosine of omega t plus the phase angle, where omega is equal to the square root of k over m, which is equal to 1.80 radians per second. We have as an initial condition that the initial position is equal to a cosine, the phase constant, and that's equal to minus a. So that requires that the phase constant be equal to pi radians. Then at t equal 2 seconds, the student's position and velocity are, first for position, 2.0 meters times the cosine of 1.0 radians per second times 2.0 seconds plus the phase constant pi radians is equal to 1.8 meters. And then when we put in the numbers for the velocity equation, minus omega a sine omega t plus the phase constant, we get minus 1.6 meters per second. The student is 1.8 meters above the equilibrium position, or 1.2 meters below the original end of the chord. Because his velocity is negative, he's passed through the highest point and is headed down. In this quick check, a block oscillates on a vertical spring. When the block is at the lowest point of the oscillations, its acceleration, a sub y, is positive because the acceleration is proportional to the negative of the position. And that concludes this video.